So let's see. Is this the actual antiderivative of our initial statement, of our initial integral? Well, let's see. So we take the derivative of this. Well, this one's going to be product rule, right? So 1 times sine x plus x cosine x. And the derivative of plus cosine x is minus sine x, and the derivative of a constant is 0. Hey, wait. The sine x and the minus sine x cancel each other out, and we are left with our original. So this formula, for lack of a better term, this technique formula, is a way to take an antiderivative of a product. All right, let's see our next one. All right, example 2. Find x e to the x dx. All right, so again, we're going to pick our u and our dv first. So my u is the one, so out of the x, and the e to the x, it's the one that when we take its derivative, it's going to go away. So take the derivative of x, we get 1. So I know that x is going to be my u. du will then be dx, and my dv will be my e to the x dx. And that makes the v the antiderivative of e to the x dx, which is just e to the x. So if I'm careful here, the integral of u dv is equal to uv minus the integral of v du. Using u's and v's, for me at least, there is kind of a flow to the way that you talk about this, and it makes doing the problems easier. It makes writing the formula easy. U dv, blah, 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 minus v du. It's a helpful way to do product rule too. You know, uv is u dv plus v du. Like, some people like that. Okay. So I got my x, e to the x, that's with the dx over here. Then my uv will be x e to the x minus the integral of e to the x du is just dx. All right, plus c. I need to take this integral. Sorry, I just got excited because like, it's working, hooray! So x e to the x, and hey, what's the antiderivative of e to the x? It's e to the x. So, and this is where there would be a plus c here because there was some integral that was taken to get to this point, but bringing in more of a plus c, you don't say 2c. Some people like to say, well, this is one constant, this would be a different constant, which is true, but essentially it's not that big of a deal because this constant is so malleable. And if I'm wrong about that, you know, if years from now you're like, Mr. Canfield, I can't believe, like, when I was back in learning integration by parts, my teacher told me that the different C's, like, who cares, whatever. And then I got, like, yelled at in college about it. Just come back and tell me so I can stop telling people misinformation. In my experience, this has not been super relevant. As long as, if you're ever trying to solve for C, you keep track of which C you're actually talking about. All right. Oh, I forgot. It actually asked another part. We could say 2a, 0 to 1, x e to the x dx. Excuse me. Well, we found the antiderivative of x e to the x. It was x e to the x minus e to the x. So then we just evaluate it from 0 to 1, right? So if I plug in 1, I get 1 e to the 1 minus e to the 1 minus 0 e to the 0 minus e to the 0. And be careful. So I'm like, doesn't everything just cancel? Just double check. So 1 e to the 1 is e, minus e to the 1 is e. So those do cancel. But over here, 0 e to the 0, that's 0. then e to the 0 is 1. E minus e goes away. Minus 1 is 1. All right. So, fun fact of the day, the integral, or the area under the curve from 0 to 1 of this curve, x e to the x, is exactly 1. Isn't that just wonderful? Oh no. Isn't that just... my math teacher likes suffering. All right. So if we're looking at our next one says x squared, the natural log of x dx. So this is where it really does start to matter, or it starts to become important to really understand which one is u and which one is v. So again, if you take that general consideration of u is going to be the one that we can take a derivative of that will eventually go away, that's helpful. So if we think about these, x squared, take the derivative, you get 2x, take the derivative, you get 2, take the derivative, you get 0. And it zeros all the way down after that. ln x, take the derivative, you get 1 over x, which remember 1 over x is x to the negative 1. Take that derivative, you get negative 1 over x squared because it's negative 1x to the negative 2. Take that derivative, you get 2 over x to the 3, right? Because the 2 comes out front, subtract 1, we get negative 3. Then we get negative 6 over x to the 4. So this one is not disappearing. This one is getting more complicated. So out of these two, I want to take the, I'm going to say that this is great. I just realized how far my foot is in my mouth for this. Okay, so u I picked as x squared, du I picked as 2x dx. Now, let me pick dv as being ln x dx. That makes v the antiderivative of the natural log of x that we don't know yet. And if you look at your book, that's actually example number 4. So I just spectacularly took my own advice and it failed. So we're gonna learn that it's what it, we'll get there. We'll find out what it is. But for now, womp womp. So my approach did not work. Let's try another approach. Let's try making u ln x. Well, that would make du 1 over x dx. Okay. So that if I make dv equal to x squared dx, what's v going to be? Well, the antiderivative of x squared, right? Which is going to be x cubed over 3, or 1/3 x cubed. Okay. Let's see what happens if I uv minus the integral of v du. Let me try setting it all up. So u ln x v x cubed over 3 minus the integral of v du x cubed over 3 d. Ooh. So let's see, on my left one, I could pull the 1/3 out front of everything and say 1/3 x cubed ln x. Over here, I can pull the 1/3 out as well. Wait, this is x cubed over x. X cubed over x will cancel, right? I didn't want to do that all in one step. Hold the phone. That integral's super easy. So I could rewrite the 1/3 x cubed over 3 as 1/9, or x cubed over 9 plus c. And everyone's different. Some people prefer having the 1/3 up front. Some people prefer it being over those things. It's because multiplication is commutative, it doesn't matter. It really doesn't. Oop, that minus sign matters though. Okay. Well, now we're going to do example 4. Some people prefer to memorize this result so that anytime they see it, they can use it and they can do it. Wait. wait. Integration by parts. Normally there's 2 things multiplied together. There's only one thing in here. ln of x is only one thing. So this problem's broken. No, the trick for this is to set dv equal to 1 dx and make u equal to ln x. If you do that, you get du equals 1 over x dx, and then you get v as being x. Check it out. If we plug this into our uv minus v integral d, whoa, Canfield, whoa. uv minus integral v du. All right. Oh, good, you didn't see me write that. uv minus integral v du, so let's see. uv, so instead of writing uv, I'm going to write the x first, but x ln x minus the integral of v du. What? This is delightful. X times 1 over x is delightful. So I get x ln x minus the integral of 1 dx. Wait, that's just x. So some people prefer to memorize this result. And if you don't believe me that this is the result, let's check it out. I'll take the derivative to see if it's actually true. So I'll take the first derivative, leave the second one alone. Looks like an h. Then I'll leave the first one alone, take the second derivative, and then minus 1 plus, oh, no, derivative c goes away. So then we get ln x plus 1 minus 1. Those cancel ln x. Cool. So this is the antiderivative of ln x. Again, some people memorize it, some people don't. It's totally up to you. It's one of those things where if you want, we could even like throw it up on the wall somewhere and you have it to stare at every now and then. You'd be like, oh yeah, that's the antiderivative of that. It's one way to memorize things is to see them a whole bunch of times. All right. So if we look at Stu's suggestion for this one, it says, sometimes you need to use integration by parts as your primary method, but use substitution as a secondary technique in evaluating the replacement integral. All right, let's go for it. Let's see what happens. So in this one, well, I know the antiderivative of secant squared x, right? That's tangent. So I'm thinking that I'm going to do that. I think I'm going to say u is equal to x. Yeah, not quite like that. I'm going to say u is equal to x. I'm going to say du is equal to secant squared x dx. This is my way that I organize this. You don't have to organize it like this. This is just what I do. So du will be 1 dx. And then here, oh, that was a v. So dv was that, so v is going to be tangent x. So let's see what happens. uv x tan x minus the integral of v tan x dx. All right. So you might not remember the integral of tangent. It's not one that we typically memorize because it's not super common for us to do in this class. So I'm going to have to find that integral. When we find it, then we'll have our answer. So just a reminder, the way that we find this integral, we can say this is sine x over cosine x. It's another way of saying tangent. And so you can set u equal to either the top or the bottom, but we find in this example that setting it equal to the bottom. Is it weird that I used u up here and I'm using u again? Let's pick a different letter. I'm gonna call it a substitution. So we'll say a is cosine x. That means that dA is gonna be negative sine x dx. So if I go and I solve this, or sorry, substitute here, we will have, oh, no, I'm supposed to solve this for dx, right? So negative 1 over sine x dA is equal to dx. So now I've got my sine x still there over a times negative 1 over sine x dA. So sines cancel, and we're left with negative 1 over a dA. So that's going to be negative ln a, don't forget the absolute value bars, Canfield, plus c. And so we'll drop a back in as negative ln absolute value cosine x. So the antiderivative of x secant squared x is this, and we can write that part now. X tan x minus, oh, that's a negative, so plus the natural log of the absolute value of cosine x plus c. It's only mildly complex, isn't it? All right, we'll get to number 6. My brain's like, I don't know if I remember this one. Oh. I figured it out. Okay, so I'll walk you through my thought process for this one. So first things first, I see this. Remember, a synonym for this was arctangent dx. It's not the negative first power of tangent. It's inverse tangent. So my first thought was like, well, is this the same as like inverse sine over inverse cosine? Am I allowed to do that? I'm not really sure what I would do with that. So maybe I could have continued down that road. I'm not sure if I was allowed to do that. I'm not confident on that. If you are confident that you can or can't, I'd love to hear from you about that. But my next thought was, oh, wait, a couple minutes ago, we did one where I had an invisible 1, and I used that for my dv. And then I thought about it, oh wait, there's a formula for the derivative of inverse tangent. So I could make inverse tangent, I could make that equal to u. If you're like, Canfield, but that's a derivative that doesn't like go away. I know, I might have had it backwards when I said it earlier. That advice isn't really panning out right now. Sometimes, such as in literally the next example, that's the way we go, but for this one, not so much. So this one, du, and so I gave you enough time. That's our derivative of inverse tangent. Let me just double check real quick. Derivative of arctangent. Yep, cool. All right. So let's see what happens. So we got our uv minus integral of v du. So then we're going to have x inverse tangent x minus the integral of v x over 1 plus x squared dx. All right. It's like, cool, we did the problem, now we get to do another problem. So I'll do my a substitution over here again. I'll say a is equal to our denominator here. So that means that dA is going to be equal to 2x dx. We'll divide both sides by our 2x. So that lets us do a nice little substitution in here. X over a. In dx's place, we got 1 over 2x dA. The x's cancel. We can bring that half out front. Sorry, now so this is 1/2 ln absolute value of a plus c. And our a was 1 plus x squared. So final answer, we can say x inverse tangent x minus 1/2 natural log absolute value of, nope, not a, of 1 plus x squared plus c. Very, very nice, relaxing, straightforward, not at all disgusting answer. All right, let's see what's next. All right, 7 integral x squared e to the x dx. Cool. Okay, so this is where, how do I know this though? Why do I know this is going to happen? Okay. I don't. I'm going to say I don't know this is going to happen. So let's say, okay, Canfield's advice has been pretty bad so far today. Let's say u is actually equal to e to the x. So du then is going to be e to the x dx. Let's say dv is equal to x squared dx. That would make our v the antiderivative of that, so 1/3 x cubed. So if I do our uv minus integral of v du, also writing that every single time you do these problems will help you remember it. uv, let's see, e to the x over 3 times x cubed, right? Yeah, okay. Minus the integral of v du. Wait a minute. Okay, so we have this thing here, but then look at this integral it's asking us to do now. This integral is worse than our original integral. That says maybe this is not the right path to go down, because now I have to do integration by parts on that integral. Okay, so how did I know that was going to happen? I think it was because when we take this derivative, it doesn't go away to a number, and this is a looping antiderivative or derivative. This just loops forever. So let's try the other setup. Let's say u is equal to x squared. That makes du equal to 2x dx. And then we'll make dv equal to e to the x dx. So that makes v equal to e to the x. So then when we do our replacement, uv x squared e to the x minus the integral of v e to the x du times 2x dx. Now, why is this better than our previous result? So the reason, because on this right here, I'm still gonna have to do integration by parts again. But here's a big difference. This is a higher power than we started with. This is a lower power than we started with. If I pick the x part as being u again, we'll get an even lower power. And eventually we're gonna be able to get rid of the x. And that's how we know, in this case, picking x squared for u is a better scenario. So let's see. Let's do it as side work over here. Oh, there's 2 in there, right? So we can pull the 2 out front. And here's where you can pause and you can say, I already did this example today. And it was number 2. So blah, 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 blah. I got that. So you can always do that, you know. If you remember the result, you don't have to redo the work. So it's gonna be 2 times x e to the x minus e to the x. And there will be a plus c, we'll write that at the very end. So I got x squared e to the x minus 2x e to the x minus 2 e to the x. And I'll throw the plus c on the end there. So there we go. Those of you that like to, you know, kind of think more deeply or see the lines on these things, I do want to throw out that there is some pattern to the way that these work, and you have likely been noticing some form of pattern as we've been going. I think that's definitely worth kind of probing a little bit more and thinking a little bit more about if you're interested. Okay, how many more egg samples do we have? Okay, so I'm gonna stop the video after number 8. I think that's all we're gonna be able to get through at this class period, you know, in one class period. But I will, I'll have the other one ready for you soon. Okay. The integral of x squared cosine x dx. All right, so again, we've got a looping derivative, antiderivative for this one. We have one that doesn't turn into a constant when we take its derivative, but that is likely the way forward here. Oh, there's the big difference. Okay, real quick. I remember my advice a little bit better now. Remember when we talked about the derivatives of ln x? They're not looping. They just get bigger and bigger and bigger and bigger and bigger. But the derivatives of cosine eventually circle around and you end up at cosine again, and it just circles through a loop. Same with e to the x. You just have the same thing over and over and over and over and over again. Because of that, that's when we know you want to have the one that is going to shrink from derivatives. You want to have that be your u. I'm pretty sure that's what I've figured out or been told. So I'll make my u x squared, make our du 2x dx. Then we'll make dv cosine x dx, make v, oh, almost wrote negative sign, sine x. All right, so if we do that, uv minus the integral of v du, so u will be x squared, v will be sine x, minus the integral of v du. So that's going to be the 2x dx and a sine x. Okay. So this one's very, very similar to one we did earlier, but I'm going to have to do integration by parts on this x sine x. So I'll call x my u, call sine x dx my dv, so that makes v cosine. No, it doesn't. Makes it negative cosine, right? Because the derivative of negative cosine gives us positive sine. So if I go in and replace everything here, uv is negative x cosine x minus integral of v du, negative cosine. du is dx. So then this is going to turn into negative x cosine x. Antiderivative of cosine is sine. Okay. So I got x sine x. When we take the antiderivative of that, we get negative x cosine x plus sine x plus c. So final answer for this whole thing here, I got x squared sine x minus a 2 outside of a negative x cosine x plus sine x, and then a plus c at the very end. And of course we could clean this up a little bit if we want to. We can say this is x squared sine x plus 2x cosine x minus 2 sine x plus c. So this is that pattern I was talking about. You might notice the 2's, negatives, and there's definitely something going on there. Oh, excuse me. So that is integration by parts in a nutshell. We have a couple more oddities that come up, which we will discuss in the next video, but this should handle a good chunk of the homework. What I would recommend is go until you start hitting a roadblock. Big roadblocks that you're going to hit are when neither derivative terminates, when neither derivative is going to go away with our looping functions. So like ln x, that's not one of our looping functions, that's not something where it's going to happen, but like when we get to like number 14, I see in number 14 e to the 4x and sine x, those are both looping derivatives. This is one of our special cases. So we've got a couple special cases we will deal with next time. And for those looping ones, I am going to teach you a special shortcut that we can do, but I want to give you a chance to make sure you understand what's going on. So hope this was helpful. I'll see you in person, or I'll see you online. I don't like it when people say I'll see you in the next video, because I'm not seeing you right now. You're seeing me. I'll see you in the next video. Bye!